So we'll start with understanding USB 2.0 core fundamentals. So basically, in this project, in this course, we are going to verify USB 2.0 core. So when we talk about USB 2.0, there are multiple devices that comes to mind. Like when I say AXI, what all things come? AXI master, slave, internet. Same way when I say USB, USB is not like you cannot say that I verified USB protocol. Protocol is rule, right? So you can't verify rule. It will be there, so you can't verify that. What is that you can verify in USB is either you can verify USB core, USB controller, USB slave device. Right? Probably host controllers are multiple types like UHCI, OHCI. I mean, again, even for controller, there will be interfaces called as controller interface. UHCI, OHCI, EHCI, something like that. Enhanced control interface, USB 2.0, universal host control interface, open host control. Yes. So either you can verify USB core, you can either verify USB controller, either you can verify USB slave device, you can verify the controller interface. So what goes into SOC is what? SOC has USB controller inside it. Then where does USB core go? All USB devices has what? USB core. Now USB falls under what? USB falls under is a very high speed protocol. Connecting through external wire. So whenever this kind of connection happens, so there is a need for something called as PHY. PHY is required. Anywhere there is a high-speed communication that happens between one block to external outside chip, right? For example, PCI Express, SATA, UFS, DDR. Even DDR actually sits where? Outside the chip only, right? DDR ports is connected, but chip actually sits outside, right? The DDR slots, whatever we buy. In all those cases, we need something called as PHY. In case of PCIe, that is called as PHY. PHY interface for PCI Express. PHY interface for PCI Express. So, for example, there will be something like DDR5. Same way for USB also, it is called as UTMI, USB 2.0 transceiver, means transmitter and receiver macros. I means interface, but it is UTM. This is equivalent to PHY. So what does PHY does? When you connect one pen drive to, laptop to another pen drive, I mean through a cable or whatever, right? The data gets transferred on the wire more like analog format, and it gets collected by a receiver, and it is converted into digital format. So that whole logic and the data will be coming at very high speed, 5 gigabits per second. If you take USB 3.0, 2.0 will be at 480 megabits per second. USB, okay, fine. So the data transfer happens at very high speed. So collect the data, there will be a receiver. Then we need to buffer the data. We need to convert. The data comes in a serial fashion. You see, USB wires, there will be only one wire. 4 wires, V plus V minus and D plus D minus. D plus D minus actually carry only single bit of data, differential format. that need to be converted into parallel format that my laptop requires. My laptop inside doesn't work serially. Laptop inside transmits the data in a parallel fashion, 64-bit fashion or 32-bit fashion. This work is done by the phi. Right? So, but our focus is not to verify phi. Phi is a different topic altogether. Phi is verified separately. We will isolate phi and verify remaining things. That is what we call USB core. Now let us understand why we need USB core. Sorry? Core and device. Device means actual functionality. Let's say you are talking about music player. Music player itself will have, let's say, pen drive which is acting like a music player. Right? You connect and let's say it plays music. It is divided into two things: USB 2.0 core and USB 2.0 slave. Like that will be the actual music player. You give the data to music player, that will play the music. So that is why we need USB core, because music player will have one interface. If you remember, take out USB music. If you take just music player interface alone, let's say you don't have USB ports. Earlier, if you remember, keyboard was connected using PS2 interface, that round interface. Even mouse was connected using round interface. Some other devices using some other interfaces. So there was no standard connection convention that some device may be connected using PS2, some may be using RS232. There were some 7-8 different formats. Then they themselves had some more issues, like each of them need to be assigned with one interrupt. Each peripheral you connect, one interrupt need to be dedicated, because anytime you get the data from that peripheral, to get the attention from processor, it need to generate an interrupt. Whereas USB 2.0 tries to overcome all those problems. Right? And also for each of them, you need to have one individual port. In earlier days, did we had a switch kind of PS2s? No, right? But to connecting one keyboard and one mouse, we need to have two slots of the ports on the device. Whereas in case of USB, you don't need. With one USB, you can use switches and all those things to connect one up to 127 devices. So that is what we will discuss. So basically, what is that USB tries 2.0 does? It tries to bring uniformity on in how the way different peripherals are connected to host. Host in this case laptop. Brings in plug and play nature. Plug and play means you don't need to switch off the laptop and switch on laptop to connect a keyboard and mouse. You can just connect and use it. And works at high speed, very high speeds. Currently we have 5 gigabits per second, right? 4.8 or something. Speed of USB 3.0. Then only one interrupt is used. Even though we connect 127 devices. That is the maximum possible. I mean, there is no, generally 127 is where you don't want to connect anything more than that, right? So that is where they are limited. I mean, this we achieve. This happens due to architecture of USB 2.0 core architecture. Core architecture is what makes this possible. This kind of high speeds. Any doubts? Core is different. Host is different. Core is like my laptop. I wrote right here. Host means laptop. Core is different. Now let us go to this. Can you read this? Basically acts as an interface for communication between host. Host is what? Laptop or anything, right? Any processor. Host means some processor, right? And a peripheral device controller. Even when I take music player has a controller which actually plays the music. Actual playing music is different and fetching the data is different. Someone need to get the data and give it to music player, right? Then music player takes the data and starts playing. So someone need to connect this my laptop to music player so that it gets the data. That role is fulfilled by USB 2.0. So where does it fit? Laptop in between USB core. 2.0 supports two speeds. This is USB 1.0 supports low speed and full speed, whereas 2.0 supports full speed and high speed. There are totally three speeds till 2.0. One is low speed, full speed and high speed. 1.0 used to support low speed and full speed. You can see it's very low, 1.5 megabits per second, 12 megabits per second, 480 megabits per second. Right now the USB 3.0 gives 5 gigabits per second. Right? So these are the components that USB 2.0 has: protocol layer, arbiter, control and status register, UTMI interface, and wishbone interface. These are the features USB 2.0 supports: device detection, speed negotiation, enumeration, normal data transfers, and suspension. Let us discuss more about these features. Typically, when we connect a device, so what happens? The device gets detected, right? So there has to be some logic which tells to the laptop that something has been connected, right? So how it works is, this document will be there, USB in a nutshell document. As I said, there are two types of devices: full speed device and low speed device. In case of low speed devices, resistor, there is a resistor which is connected to what? D minus line. To what? 3.3 volts, high voltage. Right? Whereas in case of full speed device, pull up resistor is connected where? To the D plus. Do you see D plus here? So when we connect, what happens? This connection gets established. This is my laptop, as I said. This is what? My pen drive. When I connected pen drive, that connection got established. What will happen now? Because of that, this connection got filled. This connection. Now what will happen? There is a connection between these two lines. From here to here, connection is established. Earlier, it was open, so no current will flow. Right now, what will happen? Resistance will be there and current will start flowing. So because of that, what? My host will detect that something is connected to the device. Now it sees that it is flowing on where? D plus line. So it detects that it's a high speed device. In case of low speed device, it's where? D minus. So from that's how it detects whether, first of all, it detects whether device is connected or not. What type of device is connected? Is it 1.0 device or 2.0 device? Now if it is, let's say it assumes that it's full speed device. What it has to do? So device detection using resistor connected to D plus D minus 2 VDD. Then if it is full speed, something called as speed negotiation happens between host and device, where device initiates the process. It sends one simple indication that I want to initiate a speed negotiation. If host responds back by driving chirp sequence, response back by what? Driving chirp sequence. Chirp sequence is nothing but some KJ pattern. Let us understand what is this KJ pattern is. I mean, K for some time, J for some time. What is KJ is, typically, like when we are working with very simple analogy is when you are using GVM works in what? Two modes, insert mode or escape mode. During insert you can type in, during escape you will use for some other purpose, changing or something like that. Same way, my device is either in two ways. One is either it is in the process of getting configured, or it is in the actual functional mode, normal operation mode, or some configuration mode. During the configuration mode, D plus and D minus means something else. During USB configuration, what I mean is speed negotiation, mostly speed negotiation. During this process, detection and speed negotiation. The D plus and D minus does not mean actual data, because device is still not yet configured, connected properly. So there is no point of sending D plus and D minus. Does not mean actual data. They mean what? Something related to, they carry the data to take care of detection and take care of speed negotiation. So during that time, what we do is D plus and D minus will come to how many combinations? 4 combinations. What are the 4 combinations? 0 0, 0 1, 1 0, 1 1. It is called as SC0, SC1. It is called as J. During normal operation, this doesn't make sense, 0 1 and 1 0, because it is like conflicting, right? During normal operation, either you send 0 0 on both D plus and D minus, 1 1 on both D plus and D minus. Only because we are not doing the normal data transfer, normal data operation, and we are doing some kind of speed negotiation and something not, and it can be done using other aspects also, suspend, resume. All this refers to non-data transfer modes. During all these times, you can understand D plus and D minus as what? 4 combinations. This is typically called as, is it clear to you? SC0, J state, K state and SC1, right? Now how it works is, D plus and D minus can be driven by both host and device. They can be driven by both host and device. So when I said device initiates speed negotiation process, it will send a K pattern. So device will send a K pattern to host. Host, whenever it sees, it is called as chirp K. We call it as chirp K. The chirp means this kind of repeated sending pattern is called as chirp, right? So when host sees this, host on seeing this pattern, if it is high speed capable, it sends KJ pattern. Each pattern, each K holding for some minimum time, each J holding for some minimum time. That time both have agreed. Host also knows, device also knows how much time both of them are going to hold for. Right? Since anyway there is a D plus D minus device which are connecting to host and my pen drive, it is possible, right? D plus and D minus will carry what? Either 0 0 or 1 0, 1 1 or 1 1, whatever pattern, right? And the receiving device will see that K is coming now, J is coming, right? There are 2 possibilities now, right? Totally 4 possibilities are there. What are 4 possibilities? Host is not high speed capable. Device is capable. Host is not high speed capable and device is not high speed capable. Then host is high speed capable, device is also high speed capable, and host is high speed capable and device is not high speed capable. So logically what makes sense? Which is higher speed, high speed or full speed? Which is high speed? High speed is the bigger speed, 480 megabits. Full speed is what? 12 megabits per second. In this case, what is the speed they will settle for finally? No, host is not high speed capable. Even though my pen drive is high speed, my host can't send at that rate. So they agree for what? Full speed. So device will send chirp K, but host will not initiate high speed negotiation because that itself is not capable of. Right? Now, host is not high speed capable, device is also not capable. Finally, they agree for what? Full speed. Right? Host is high speed capable, device is also high speed capable. What will happen? So, host will send KJ pattern on seeing chirp K from device. Then, device will drive a port by name transceiver selector, no, termination selector to high speed. By default, it will be in what? Full speed mode. It will be change it into what? High speed mode. It's a 1-bit signal. 0 means high speed, 1 means full speed. It will, by default, it will be high. Whenever it agrees that I have got 6 patterns, why it should do that? We need to be sure that we have sent 6 patterns, KJ, 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 like that. If you, let's say, after only sending 2, if you stop, should it mean negotiation complete? No, right? So that process will, that is where we need to acknowledge. So here there is no request and acknowledgement, right? There is no request and acknowledgement. Everything has to be done through this D plus D minus and some this kind of lines. In this case, what? Device is not high speed capable. Device host will send KJ KJ, but device will not drive termination select to high speed. Is it clear to you? So other than that, there are USB core can be in multiple states of operation. Can be in multiple states. What are the states? Detected. It is either in detected state, attached state, reset state, suspended state. Yeah.
Since this data schema to be differentiated, how can you drive the 0, 0 or 1, 1?
It is possible, right? I mean, during
configuration line, it will be differential.
No, even though it's differential, I think, the mode will tell that. There will be line, there will be something called as line state signal. UTMI interface has line state signal, which is again 2 bits. It will tell whether normal operation, those things it will tell. I'll show you that document also, right? So through which the receiving device will understand whether it's a normal operation. Should I treat it as differential data? Or should I treat it as normal? Normal data, right? Speed negotiation. Then all these things, right? Whatever you see, or is it in the chirp detection process? So here itself you see around 6 possible states: detected, attached. Then there can be again what? Detached. These are all possible states, right? Even though they are very simple, right? So to manage all these things, USB core will have a state machine with some rules. When will I move to suspend state? When will I come to resume state? When will I start speed negotiation? When will I agree that high speed is done? So that whole thing is explained in a document known as USB code. It's like a big state machine where it starts with reset. It moves to immediately full speed mode. Wait for 100 milliseconds. Wait for J accepted. Then set in attached flag indicating the device is attached. Then go to normal operation. Then there are two reasons why it can move to either suspend state or reset state. Or if this condition meets, it will go to suspend. If this condition meets, it goes to full speed and wait for 100 microseconds. If this condition meets, it goes to reset state. Once it is in reset, once it is in suspend, what it does is explained again. If you meet this condition, it will go to reset. If you meet this condition K asset, it will go to this K state. If you meet this condition, it will go to this state. Like that, it again goes to normal operation. So like this flowchart explains how it moves from different one state to other state when we control two variables called as line state and D plus D minus. There are two things, line state, D plus D minus. This will explain all those things. So for example, it enters into reset state, let's say. In reset, if you send chirp K, device will send chirp K, then you start waiting for KJ pattern. How many times? 6 times totally. Chirp count of 6 times. If it meets that 6 count, then it moves to what? Normal operation. Sorry, it switches to what? High speed mode. Then you give SC0. SC0 means what? 0, 0. Both are 0, 0. Then it moves to what? Normal operation. You drive 0, 0 to indicate that I am done with this process of configuration. Now it's time to move to what? Normal operation. So the document clearly explains how you move into speed negotiation process, how you move into suspend state, how you move into resume state, how you move into normal operation. Everything has been clearly explained in the document. So just that you have to understand who will drive chirp K, who will drive these things. There are only two things, either host or device. So you are mimicking not the device, you are mimicking what? Host behavior. Because I am verifying what? Device. When verifying device, I can't become a device. I have to verify device, I have to work like a something that drives device. That is what? Host. So in my case, I will implement this portion. I will drive KJ pattern. When will I do that? Whenever I get chirp K. So this kind of thing I have.
Normal operation is enumeration after doing the enumeration.
No, even enumeration is normal operation. Enumeration is where I will talk about that. Is it clear to you? So then, what is the next state? Next process? Enumeration. What is enumeration? Let's understand. Whenever you connect any pen drive or any USB devices, you see that automatically device gets detected, right? Then it will detect what is the manufacturer name, what is the type of device, what is the memory, any other characteristics that are useful to the user. That user needs to know, it will give. But there will be some internal things like how many endpoints are there, what is the type of endpoint, whether it's in endpoint, what is the direction of endpoint. That we as a verification unit probably may be interested, but not the other customers who buy USB2 just to do the usage, right? They don't be worried about what is the technical details of inside. That is what internally USB controllers will take care. USB host and all those things will take care. But as a user, you will come to know that. So all this information about the USB core is stored in something called as device descriptors. Inside USB core has complete information about USB device. Lot of things. I mean, what is the type of device, what type of registers it has got, what is the data direction type, lot of things it will have about the device. All that information is read. The process of host or USB device drivers reading device descriptors from USB device is called enumeration. What is it? Process of host reading device descriptors from USB device is called enumeration. Right? So once it does this thing, so what is the order in which it happened? Detection happened. Then what? Speed negotiation happened. Then what? Enumeration. So during enumeration, host will assign one unique 7-bit number to each connected device. So 7 bits means what? 128. 0 is not used. So how many are remaining? 127. So 127 devices can be connected maximum to the laptop or host. Then what it does? It will understand, host will know type of device, number of endpoints. What is endpoint? I'll explain. It's like a channel that connects my laptop to the device. More endpoints means more throughput, you possibility of getting more throughput out of that. Number of endpoints, all the endpoints, type of endpoints, etc. Direction of endpoints. So even this information is present in the nutshell. You go to the one chapter called as device descriptors. It's a short document, 30 pages. So device descriptors are what? Configuration descriptor, configuration descriptor. Again, interface descriptor, endpoint descriptor. You see, I was telling about endpoint information, right? So all this register information is read by my host during the process of enumeration. Because unless my host knows what type of device is connected, it won't be able to figure out what type of information should it send to the device. So the process of reading that information is called as enumeration. Enumeration is done using a type of transfer called as control transfer, and endpoint 0 is used for this purpose. What is the transfer type? Control, and the endpoint number is what? Endpoint 0. So once it is done, next step will be data transfer. So it's like if there are 3 devices connected to the laptop, each device is given with what? One unique address number. Each device has device descriptors, unique descriptors, right? Where does those descriptors come from? Manufacturer would have hard coded them. It's like you can say ROM inside my pen drive will have those descriptor values hard coded. Everything is kind of, you cannot change those, right? When you connect, my laptop will read all that information and then figure out that this is the name of device, this is a manufacturer, this is the type of device, this many endpoints it has got, this type of transfer only it supports. Like that, it makes a table of everything. So by this stage, what? By the time of enumeration, everything about all the connected devices are known, and it is dynamic process. Anytime you connect a new device, that enumeration will happen again for that newly connected device. Then what will happen? Data transfer. Who will initiate data transfer? Host. To the host, who will initiate? Application level, right? Application layer will initiate data transfers. What does it mean? When I connect pen drive, from the operating system only, I will say that move data from my laptop to pen drive. Inside hardware, I don't do, right? At application level, I do that. Whether you want to play a game from pen drive, whatever you want to do, it's application kind of. Then it goes to software layer. Then embedded layer. These instructions, what we have to do, whether we want to transfer the data from laptop to pen drive, pen drive to laptop, everything is initiated at application layer. It goes to a software layer, then it goes to a embedded layer. Embedded layer here is nothing but USB device drivers. USB device driver is not a hardware. It's a software that gets installed when I connect my pen drive to laptop. So what device driver will do? Device driver has all the information about all connected devices. It knows in and everything about all the devices. Now let us say 3 requests come from application level. One for pen drive, second for music player, 3 for printer. One pen drive, 2 music player, 3 printer. Now there has to be some priority level that my laptop has to work at. Right? Which one we should get the priority among all this? Generally, music player. What will be the requirement generally? Needs data on continuous basis. Printer. Does printer need data on continuous basis? Only at discrete times. But huge data it requires. It requires a lot of data because printer means it will be megabytes, something like that, right? And what about pen drive? It could be either continuous or discrete, depending upon what kind of device, how it has been configured as. Okay, so these kind of devices which require data on a continuous basis are called as isochronous transformers. Printer are called as bulk devices. There is another kind of device that comes to mind, that is the keyboard kind of device, keyboard and mouse, where they have to give the data, but they can't generate interrupt because there is no interrupt present in my mouse. As I said, there is only one interrupt, right? So in these cases, devices which require polling at regular intervals or interrupt based. 3 kinds of transfers. One is what? Isochronous. Second is what? Bulk. Third is what? Interrupt. Fourth category is anyway we have seen, that is what? Control transfers. Control is for what? To read and write the during the enumeration process. So then what will happen now? The USB 2.0 during full speed or high speed will put some requirements on how much bandwidth should be given to, how much bandwidth to be given to ISO, bulk, interrupt. For example, in full speed, ISO is minimum 90%. Interrupt is 10%. So, do you get any bandwidth for bulk? No, right? Already 100% is done. So, bulk will happen only when there is no ISO or interrupt. At least ISO. If there only when there is no ISO, bulk will happen. Same way, high speed also will have some requirement. I guess ISO will be 80%, interrupt is 10 and something like that, maybe 10%. These things, the USB core rule, spec will tell you clearly. Even our document, this document will clearly tell What is the requirement? Not sure, not here. Somewhere I'll point you to the specific thing again. Is it clear? So now these two lines are inputs to my device drivers. These two lines are what? Input to my device driver. Let us say device in what? Full speed mode. It got requests for what? Pen drive, music player, and printer. So now what it should do? It should allocate enough bandwidth to whom? Music player. If there is anything remaining, then it should go to whom? Pen drive or printer. Let us say pen drive also be classified as isochronous. Then it will also get the data sharing basis. Some amount of time it will go to whom? Music player. Some amount of time pen drive. So all these data transfers happen using USB. Using USB frames. For full speed, it is called as frame. High speed, it is called as. The duration is 1 millisecond. The real lifetime, the real life 1 millisecond, whatever is there. For that much time, one frame will go. If you count 1 millisecond, whatever time it is, during that time, one frame will go from laptop to pen drive. Next 1 millisecond, another frame will go. Whereas in case of micro frame, it is 125. And frames are like packets. I'll tell you, frame itself consists of packets. And each frame, each micro frame carries 5 times more data than frame. So it is 5 multiple here. Here it is what? 8 multiple. What is 8 multiple? Here it was taking 1 millisecond. Here it is taking how much? 125 microseconds. Multiple is how much? 8. And it is carrying how much more time more data? Even though it's smaller, how much time more data is carrying? 5 times. So it becomes what? 5 multiple. So totally it comes to what? 8 into 5. 40 times. 40 times more faster than full speed. Full speed is how much? It comes to what? Any doubts you have from this point? See this 12 Mbps, 480 is for USB wire level, 5 wire level. When D plus D minus will happen at this level. You see this is very high speeds, right? 480 Mbps means you need very high, very advanced logic to connect. That is where 5 will come. Whereas inside my laptop, it is not D plus D minus. It is what? Some parallel data. Those data are two types. This above serial data is converted to parallel fashion. By whom? UTM. There will be a serial to parallel conversion. When you are driving data to outside world, parallel to serial conversion. So it is either 8-bit format, 16-bit. If it is 8-bit, let's say, what should be the speed? Can you tell me? Each bit that is coming, every 8 bits you are driving as one byte. How much should be the speed of UTM interface? If it is at 480, then 480 hertz or 480 megahertz, it should be what? 480 by 8, 60 megahertz. If it is 16 bit, speed of UTM interface clock should be how much? That is only then it will be able to satisfy that requirement, right? Let's say it is working at 20 megahertz. Will it be able to collect all the data and give it to upper layers? No, right? What will happen in that case? Buffer will become full, right? Because you won't be able. UTMI is not pulling at the rate at which data is coming in. So these 60 megahertz and 30 megahertz are generated by phi internally. Phi means what? Using clock extraction lock. Inside phi, it will have a logic to extract the clock. It knows what rate bits are coming. Using that bits, it knows what is the speed. Is it 12 megabits or 480 megabits? Accordingly, it will convert. It will either try to generate a clock of 30 megahertz or 60 megahertz. Why we need this clock? Because at UTM interface, you need to transfer the data, right? It is not anymore serial fashion. It's like this is what I am calling as phi. On one side, what do you have? D plus D minus and V plus V minus. Is there any clock here? Sorry. On USB side, is there any clock? No. Whereas here it is not anymore serial. It is not D plus D minus. It is converted into D plus D, 8-bit data and 16-bit data format. So here there will be something called as clock will be there. At this UTM interface, clock is required. That clock, who will generate? Outside world or phi? In this case, phi itself will generate and give it to the UTM interface that required. Any doubts you have to this one? So then, what does it do? Each frame, let's take a frame or micro frame, whichever you want to take. Let's say micro frame. How much is micro frame? 128 microseconds. And what is the speed? Frequency? 480 megabits per second. So 125 microseconds will have how much? How much data? 480 into megabits means how much? 1024 into 1024. Divided by how much? Each second has this much data. And 125 microsecond is how much? 1 by 8 millisecond. Right? By 8,000, 1/8,000 of second. So how much data do you have? By 8,000 bits. Which is how much? 480 by 480 into 1024 into 1024 divided by 64,000 bytes. Is it clear how I came up with this? This is the data that will be there in 1 second. Because it is what? 480 megabits per second. In 1 microsecond, 125 microseconds is how much? 1 second has 8,125 microseconds. If you multiply that, it will come to that one, right? Is it clear? Bits. If you multiply it by 8, it will become 64,000. 8 bits are 1 byte. 8,000 bits are.
Shouldn't we convert that bits by logic? So
Bits is in the upper level. Let's say it came to 480 into 1024 into 1024. These many bits are there totally in a second. 1 second has how many bits? 50, 331, 6480 bits per second. 1 millisecond, how many? 50, 331, 646, that's all. 0.480. Dividing what by what? 1000. Now 125 microsecond. 3316.48 divided by how much? 8. These many bits. In terms of bytes, divide again by what? It comes to something like divide by 64. If I divide this by 64, it comes to 7864 bytes. Per micro.
The person you are speaking with.
Sorry? So what device driver will do? Device driver has got request from application level. It knows that it needs to allocate some data to whom? Music player. It needs to allocate some data to whom? Pen drive. It needs to allocate data to printer. It sees who is high priority. Music player is high priority or which one? How does it make that rule? Not by the name printer or not by name music player. It knows something else. What is the type of device? Is it isochronous device which requires data on continuous basis? Is it bulk device which requires only at discrete times? Is it an interrupt kind of device? So for interrupt, what happens is data packets are generated once every 10 or 100 packets frames, etc. Not every frame you generate the data, only very discrete times, because you can't operate the device at such a high speed. You can't be operating at microseconds, millisecond level, right? So even if my laptop holds my keyboard once every 10 milliseconds or 100 milliseconds, that is good enough for that to be detected, right? So keeping all this in mind, it creates device driver will create frames. What is frames will have? SOF, start of frame packet, followed by series of token packet, data packet, can you read it? Any doubts here? Like series of is an SOF packet. Now SOF packet is also clearly defined. SOF packet is 3 bytes size. There is a very defined pattern. It starts with something called as PID. PID stands for what? Packet identifier. You need to tell what packet is it. Is it SOS packet, token packet, data packet, handshake packet, special packet. There are 16 types of packets. Then frame number. Which frame number are we? Am I sending first frame, second frame, millionth frame? Because data, let's say when you transfer 1 gigabytes of movie, can it be done in one frame? Right, one frame will only carry how much? Hardly 7,000 bytes. Whereas 1 gigabits means what? Some millions of bytes you have to carry. So they cannot be done in 1 or 2 frames. So each frame needs to be done. So frame numbering, why is it important? Receiving device should know whether am I receiving frames correctly or not. Am I missing any frames? The frame number will tell to the receiving device that it will be how many? How many bits? You understand why 7 bits are required? Because the huge number of packets you have to send. Then what? Yeah. PID is 8 bits, but how many combinations I said? 16 combinations. It's like PID, inverse of PID. So PID itself self-check itself. Let's say PID 1 bit is correct. Other part of PID will tell that this packet is corrected because PID did not come. Then token packet. What is it? 3 bytes. Again PID. How many bits? Then what? Something called as address. Because laptop when generates the frame, it will send the frame to my pen drive also, music player also, printer, wherever, whatever device is connected, it will broadcast the data. Like host will broadcast data to everyone. My device should tell whether should detect whether is this device data to me or not. This address will help it detect whether it is correct. This how many bits? 7 bit. I said that when during enumeration, host has assigned 7 bit number to each connected device. This 7 bits it will compare with whatever 7 bits it has got stored in. Then it will know whether this token packet is it for me or not. Then along with that there will be something called as endpoint. 4 bits. There are 16 endpoints that are possible inside each pen drive. Maximum. But it is not a rule. You can have device with only 2 endpoints, 3 endpoints, 10 endpoints, all that. More endpoints means more throughput you will get. More data transfer is possible, theoretically. Then you will have what? CRC. If you add all these things, that again comes to about 24 bits. Then data packet. Size depends on type of transfer. For example, PID is again 8 bits. It's array of bytes. CRC 16. Because we are sending bigger data, we send what? CRC 16. Now, size depend on type of transfer means what? If you go to this one, it says that clearly. For isochronous, maximum size can be 1023 in full speed. In high speed, it can be 1024 bytes. In interrupt for 64 bytes is the maximum possible. High speed 1024. Is it clear to you? What I mean by size of transfer here? Data packet size is depending upon whether are we doing isochronous, interrupt or bulk. For example, for interrupt, do we need to send a huge packet? No, right? It's only reading some bits or bytes of information. So for that reason, they keep it smaller, 64 bytes. Whereas for a music player or something, you need to send bigger amount of data to play the music. For that, they have allocated bigger data. Then what? Handshake packet. Handshake packet is only PID. It will tell what type of handshake is it. Is it acknowledgement handshake, no acknowledgement handshake, stall handshake, those kind of things. Any doubts in this? So, what will happen? Server will send frame to USB controller. Controller will convert this frame into USB interface format, sends it to whom? File inside laptop. Even laptop will have a file. Then file will convert detail pattern, drives it on D++. Then on the other side, file will collect data. First, what will come? Serial fashion. Convert it to parallel pattern. It to USB. Then, when USB core receives SOF, first what it will do? It does SOF specific checks. What are the two checks it does? One is frame number. Is the frame number continuous or not? PRC check. These two checks it will do. Is it clear why it has to do all these checks? Who is sending SOF? My laptop is sending. Converting into serial pattern, sending it. Then other side you again collect. Again you convert to parallel. Right? You may say, why can't I generally connect parallel itself? Why I can't do? We are going through parallel to serial, serial to parallel, but finally data is same. Why I can't connect parallel only? Data bit will be more, right? Here it is only 2 bits is enough. 1 bit is actually D plus D minus 1 bit is enough. Whereas in case of if I connect 16 means 16 bytes, so it will be much bigger, right? And also it is prone to that interference and lot of other issues, right? Then what will happen? Then host will then send what? Token command. Device will figure out is it will be for one of the devices, not for pen drive. It may be for music player, it may be for printer. If it is for, let's say, for me, then I will proceed further. I will process next data packet and next handshake packet. If it is not for me, I will not process following data packet and handshake packet. It's like a group. Token packet, data packet, handshake. Token packet will tell whether you should pursue the packets or should not pursue that set of packets. But when next token packet again comes, we will again process. Right? So then, if the packet is for same device, it will make note of endpoint. There will be endpoint number, 16 possibilities, 4 digits. Yeah.
So, the first point you are saying that USB core receives SOF, right?
Yeah.
So, will all the USB device does will do frame number checking? And
Yes. That it logically makes sense, right? It can't be like a, let's say pen drive is connected, something else is connected somewhere. It can't. It will not skip. It will skip on something else. Everyone will do that. Right? Host. Then what? Host knows whether it is giving data or expecting data. It is possible, right? You can read from pen drive, you can write into pen drive. So that is where comes the concept of in endpoint in case of giving data, what endpoint is targeted? Out endpoint. Now endpoint number itself tells to device all this info, like type of endpoint, direction of endpoint, everything about endpoint will come to know only by endpoint number. So further there will be something called as registers. Endpoint CSR register, endpoint interrupt register, endpoint buffer 0 register, endpoint buffer. For each endpoint, for 16 endpoints, how many registers will be there totally? 64 registers, 16 into 4. What is that each register will tell? Let's say if I take endpoint 0 means it will tell about endpoint 0, what type of endpoint is endpoint 0, what type of transfer it supports, what type of direction it supports, right? Then each endpoint is associated with a memory. It's not the memory which you are talking about, my pen drive memory or my this thing, actual device memory. It's internally there will be every core will have something called as SRAM. It's for temporary data storage. That is where endpoint brings the efficiency of data transfer. We'll discuss about that. Right? So then, let's say if host is giving data, device will get the data packet, extract data, store it temporarily in SRAM buffer. EP buff 0 or buff 1 will tell where in SRAM. Then what does it do? It will generate a DMA request. Who will generate DMA request? USB core generates a DMA request to function controller. So the third one, function controller here is the USB slave. Host, core and slave. Then USB slave will complete the DMA by reading SRAM data. If it is second case, what is the second possibility? Host is expecting data. Let's say device will frame the data packet. Device has to create the data packet. When my laptop has to get, who will give the data? Device has to give. So where does it get? It gets it from SRAM. Who has written it? USB core has generated DMA request to function controller. USB slave will complete request by writing data to. In one case it is reading from SRAM, in another case it is writing to SRAM. How does it know whether to write to SRAM or read to SRAM? The endpoint number will tell. The most critical point in all this operation is what? Endpoint number. Each endpoint is associated with registers. That registers will tell what type of endpoint. Is it isochronous? Is it bulk? Is it interrupt? Is it control? Is it in? Is it out? What is the memory space that should be used? All that information that endpoint number will tell. So this keeps happening. So once this is done, once this data transfer is done, data packet transfer is done, the DP receiving device or host, whoever it could be, will generate handshake packet to indicate successful completion. Any doubts to this point? So this is how it keeps happening. So now this is the normal data transfer. Then what is the remaining thing? Suspend. There has to be some rules which will tell when we suspend. Why this suspend operation is required? Why should we suspend the device? To save the power, right? Ideally you want to save the power. Power is very important aspect. You want to save the power. So what should be the rule that will tell when should we suspend? Something like say 3 milliseconds. Some rules will be there which will tell when I should initiate suspend operation. So it will automatically enter into suspend state. No data transfer, it is idle means suspend state. Then there will be some rules which will say when it will resume. Anytime some data comes, automatically it will resume. So resume also whenever data transfer request is initiated. So that is where these flowcharts will explain. I was showing this flowchart, right? Will explain how it enters to suspend, how it enters to resume, how it enters to reset, how it enters to speed errors. Everything is clearly explained in this, right? See, everywhere you see SC0, HS, K state, SC0, right? J state, idle. I mean, there are only two things: line state and this KJ patterns, which will govern what you want, whether you want to put in suspend, resume, all those things. Any doubts till this time? Can you please read this one? We read till this point. We discussed the device detection, speed negotiation, enumeration, normal data transfer, suspend and resume. In normal data transfer, what are the two speeds possible in 2.0? Full speed and high speed. Full speed and high speed, both devices know. Even my UTMI know what speed I'm agreed for. Full speed or high speed. Accordingly, it will generate a clock at that specific frequency. It will either generate clock at 30 megabits, 30 megahertz, 60 megahertz, or even lower if it is full speed. Accordingly, it knows what data, what speed I have to collect the data. Everything it clearly knows. And it sends the data. If it is full speed, it will send data accordingly to the device, my core. If it is high speed, it will send accordingly. And suspend and resume also, as I explained, they will happen on some specific condition basis. Can you read this one? Device detection speed. Any doubts here? Can I go to next slide?
I think that LS means 1.5 ABS, right? So that is USB 1.0.
Yeah.
Every USB 2.0 device is classified as LS.
I think it could be my mistake. Maybe just support this. Right? Can you read this further? Enumeration. Any doubts here? This is a continuation of same. So always, who will generate the frames? Host. So USB is a host centric. Means host is the one which acts like a master. Even though it is interrupt, right? Keyboard has to give the data. Host is the one which generates interrupt packet. There is nothing like interrupt packet or isochronous packet. The packet is defined as interrupt isochronous depending on what? Which endpoint is targeted. Endpoint is classified based on what type of transfer it supports. So my laptop knows if I have to read the keyboard, it has got two endpoints, endpoint 2, endpoint 3, let's say. So to read the data, I need to generate a request on what? Endpoint number 2, because endpoint number 2 is what is in type of endpoint. It knows because it did what? Enumeration on all the devices. It knows that information. From that, it creates the frames. If it is 3 is, let's say, endpoint number, which is in. So it will generate token packet with what? Only endpoint number 3. Let's say it has to give the data. It can't generate endpoint number 3. So that is where device drivers come into picture. They knows all the information. They accordingly know whether I need to read or write. Do I need to do isochronous or bulk? Accordingly, they will choose the right set of endpoints. So once you are done with reading, I'll explain this. So, any doubts till this point? Now let us talk about this one. If you take this diagram here, there are two connections possible in this. One is here, one is here. This represents what? 5 to 5 communication. What is that communication? 5 to 5. One side is 5, other side is also what? Right? Is there any request and acknowledgement? Is there any request acknowledgement signals here? No. So to one file to tell to the other file that I am sending a packet, I am sending a frame, it uses a pattern called as sync. It's a predefined pattern. Both sending device and receiving device knows what does that pattern mean. That pattern is not the data. That pattern is only for the receiving device to know that some packet is going to start now. So in case of all the packets, this device 5 is going to send packet with 5 sync appended in the beginning, and in the end of packet it will send another pattern called as EOP. Sync is 7 bits, I guess 7 or 8 bits. EOP is 2 bits. Through that, receiving device knows that packet is starting, packet is ending. Whereas here we don't need that, because there will be some signal called as valid. Like we have in AXI protocol, valid ready will be there. They will be there because it's a parallel protocol. It becomes more like a AXI protocol. I mean parallel communication protocol. Whereas still here it is what? Serial. So both devices need to communicate through sync and end of packet to tell to each other that some packet is starting, some packet is ending. Because there is no signal to say that packet is valid now. Because everything has to be communicated through only on D plus D minus. Whereas here there are dedicated signals like valid, ready, transmit ready, RX valid, RX active, something like that there will be there, which will tell to the both devices that some packet is coming or it's not coming. Hence you don't need to send what? Sync and EOP here. Whereas here you need to do what? Sync and EOP. What is that we are modeling at? Are we verifying at this level? At this level. UTMI level. So do I need to worry about sync and end of packet? I don't need to, because that is taken care by 5. I am not verifying 5 here. So for me, sync and end of packet is out of picture. Only thing I know is what? SOF means what? Frame number, PID, frame number, and CRC. Token packet means what? PID, address, endpoint number, CRC. Only those things. There is no sync, no end of packet. But someone who is verifying at 5 level needs to worry about sync and devo. Can you read this from here? Any doubts here? I'll go to the next slide. Then frames go to all devices connected to host. It's like a broadcast. Frames are broadcasted everywhere. USB 2.0 uses address field in the token packet to figure out if the packet is intended for it or not. SRAM in USB 2.0. Can you please read this one? What is SRAM is used for? Temporary data storage. It is not the pen drive. Let's say when I say 16 GB pen drive means SRAM is not 16 GB. SRAM is a smaller memory. What is the benefit of SRAM is, if you take here, when, let's say, out data packet. Means who will give the data? Host will give to pen drive. This is the source. What is the destination? Actual destination? Ideally, data should go where? Like this. Here. But the problem is, for some reason, if it is blocking, it is not accepting this data alone, it won't be able to send other data because it blocks this. If this is the only link possible, it will block. Now what happens is, this is not followed. Whatever data comes, goes here, it doesn't give directly to here data. It stores the data to some location in S1. That locations are what we are calling as buffer 0, buffer 1. There, even buffer 0 has two things. What is the pointer? What is the size? What is the pointer? What is the size? Accordingly, it knows where to stop putting the data, then where to wrap back. It is not infinite memory, right? It will start writing, and once it reaches upper boundary, it comes again to lower boundary. Like that, this is divided into 32 regions. Why 32 regions? 16 endpoints. Each endpoint is how many buffers? 2 buffers. So 16 into 2 buffers. And there are registers here. There we clearly tell what is the buffer 0 start, endpoint 0 buffer 0 start, endpoint 0 buffer 0 start size. Then again we say endpoint 0 buffer 1 size, buffer 1 start. Like that, for 32 regions we have size and everything, size and pointer. Then it not only writes the data here, now it needs to tell to the function interface that I want you to read the data. It generates a DMA request. To whom? Function interface. Then function interface knows that there is a DMA request. DMA request is also comes on what? 16 bits. 1 bit for each endpoint. Now this device will know that request is coming for what? Endpoint number 2, 3, 4. 2 means it knows out endpoint. Means what? I have to go and read the data from where? SRAM. It knows what is the buffer location, what is the size of buffer, everything it knows. What? Function microcontroller. It goes and reads from, it gets the data. This process keeps happening till the time my host keeps giving the data. When will it stop? When it stops giving data. What will happen when it stops giving data? DMA request is not given anymore. So when DMA request is not given anymore, it won't do any DMA reads anymore. Let's say again it initiates a read request. It is possible that one point you may be writing to pen drive, same point you may be reading from pen drive. You can do, right? Though it reduces efficiency very much, you can connect a pen drive, you can transfer movie into pen drive, you can read some other file from pen drive. It is possible. You can try that, it's possible. So same frame, and you will see that it happens parallelly. It's not like one will finish, then only new will start. They will have to happen parallel. Say 16 minutes to complete this, 10 minutes to complete this. Just that the time increases a lot. If individually it had taken 4 minutes, concurrently if you do, it may take 6 minutes, right? It takes more time because lot of additional this goes in this sharing, multiplexing, right? So each same frame may have data packets targeted towards reading the device, may have another set of packets which are targeted towards writing the data into device. In one case you will use one endpoint number, in another case you will use another endpoint number. U means what? Who decides all this information? My host will decide. Host has device driver, which is getting requests from where? Application level. Through that application level, it knows what is the priority of each application request. Is it for music player? Is it for pen drive? Is it for printer? Is it for keyboard? Accordingly, it knows. For keyboard, you don't need to get request from up, right? It already has a counter, some kind of counter have generated now. Next, I will generate after 50 frames. Next 50 frames, like that. Accordingly, keeping all that information, it keeps generating frames or microframes. So in this case, you will see the beauty is even though the D plus D minus lines are only 2, you don't have D plus D minus for transmit and receive. Same will do transmit and receive. In 1 millisecond or in 125 microsecond microframe, sometime it will be transferring data, sometime it will be receiving. In microsecond, you can see how efficient phi should be. It is finally done by whom? Phi, right? Phi is the one which is taking care of all these requirements in how much time? In 125 microsecond. once it is getting SOF, once it is getting token packet, let's say it's a in request, it immediately has to send what? Data packet. Then it has to expect what? Handshake packet. That all happens in how much time? 125 microseconds. So that keeps happening. So that much efficient phi has to be. So in case of read, what will happen? Again, token packet goes here, token packet went. It knows that token packet came with what? Endpoint number 3, let's say. 3 means what? My device knows that it is read request. So it immediately goes and performs a read from here. But let's say data is not there. What it will do? It will initiate a DMA request. It will understand that endpoint number 3 means what? I need to give the data. So what it does? Will it give data to VL or will it give data to SRAM? It will write into SRAM. So you see, SRAM is accessed by how many people? How many blocks? Protocol layer and function controller. So there is an arbitration required. That is done by whom? Arbiter. So then it will read the data, whatever data came, read the data, and frames the data packet. It will create the data packet. PID data CRC. It will drive the data packet. Then it will convert into serial fashion and send it. Then again, other side, phi will collect the data in serial fashion, convert to parallel, give it to processor level. Then it will again send what? Handshake packet. Handshake packet is only stops at where? Protocol layer, just to know whether things happen successfully or not. Any doubts here? So that is what SRAM is. Can you please read this? So what is the critical thing in all this SRAM communication? Endpoint, number of endpoints, endpoint number 2 or 3 or 4. In case of protocol layer, in my core, there are registers, 4 registers. What are registers? Endpoint, CSR register, interrupt register. Why we need interrupt? Let's say endpoint is isochronous. You are targeting bulk item. Something, you are doing something else, something which is not supported. You need to raise some alarm, right? That is why we need interrupt register. Right? Then we have buffer 0, buffer 1. What each buffer will tell, register will tell, what is the address current, where are we currently, and what is the size of buffer. Same for buffer 0, buffer 1. Can I move to next slide? We'll do little longer session and we'll stop the session today. Some work. So I'll give these documents to you. So please go through the documents today. I'll complete this whole USB operation. So tomorrow when we start with the actual coding or listing of features, test plan, if you have done your self-reading, it would make it easy for you to understand this. Right? So how DMA transfer works in USB code? So why do we need 16 lines for DMA request? 16 endpoints? Because if you use only one DMA request, what is the problem? If 2 transfers came on 2 endpoints, how does controller know for which endpoint is the DMA request? Now how this 16 endpoints is making transfer efficient, data transfer throughput increasing? Let us say my host is not able, my controller, this one, let's say one request came on one endpoint. Let's say one request came on endpoint number 2 and it initiated DMA request. let's say for that specific request, my function control is not ready. It doesn't have either it doesn't have the data, it doesn't want to accept the data immediately. For some reason, I mean, microcontroller, we can't tell how microcontroller is going to behave, right? It can behave differently for different types of requests. In those cases, what it will become? It will become blocking point. If you don't have concept of endpoints, only one channel is there, let's say, what it will do? It will block everything, because unless it is cleared, new request cannot generate. Now what will happen because of this concept of endpoint? Whatever data that was coming, you are storing it and you are initiating DM request. Till the time it doesn't give DM acknowledgement, this data will present here only. It won't go anywhere. But what is the additional benefit? You are not blocked. You can generate a new request. It will be stored in a new data location. It will generate another DM request. Let's say my microcontroller is ready to respond to that. It will go and read this data. So while the first request is hold, second request can be completed. It all depends upon how microcontroller is behaving. So this is for two endpoints. If I have more endpoint, what is the possibility? More this kind of flexibility I will have. So more data throughput can be achieved because nothing is becoming blocking. Yeah, hello, tell me. Any doubts here? So USB core generates basically two interrupts. Not to the host, not to my laptop. It generates to function control. Inside the pen drive itself, as I said, there is this function controller. This function controller, interrupt will be generated. My function controller, microcontroller will decide what to do with interrupts. Right? Going forward, we will understand why interrupts will be generated. Interrupt can be generated for many reasons. PID is not correct, CRC error happened, data packet did not come, some device got disconnected, device got connected. All these reasons, interrupt will be generated. Interrupt is a way of giving attention to the microcontroller, saying that something has happened, something newly has happened. Right? Error has happened, or some device got detected, something. So it's up to the microcontroller to decide how it wants to deal with it. The function controller handles this interrupt based on what? Interrupt type. What type of interrupt is it coming? Is it interrupt specific to endpoint? A lot of things. This is the architecture. Now it should be clear to you what block does what. So essentially, what is my USB core is all about? Solely any doubts here? This is not my core. This is also not my core. Function interface is also not my core. So totally, how many interfaces do you see for that green block? 3. 1. This is for what? Doing speed negotiation, device detection. Ideally, device detection completes here. So this interface is out of picture for device detection. So we don't need to do device detection checking. Speed negotiation involves here because device is the one which has to send what? Chirp K. Right? Device is the one which has to achieve the KJ pattern. Then it has to agree whether it agrees or not. Then data transfer. Also, who has to do? This one. And suspend resume, even this one. What about function interface? Ideally, in real life, when you buy a pen drive or anything, these descriptors, right, registers and all those things are hard coded. They are already programmed into the pen drive because the manufacturer of the device knows why this device will be used. For a music player, he won't keep interrupt kind of endpoint. He will only keep what? Isochronous kind of endpoint. So you would have programmed all that information accordingly. Whereas when we are verifying our core, is this core only meant for music player? No, right? It can be used for different requirements. So I have to program these registers. That programming I will do using this. Registers are there. I need to program, because if it is only for one requirement, no need to program. We can just hard code them and verify them. If it is for different requirements, I need to program for different test case requirements. So some endpoints I want ISO, some bulk, or I want one test case where all 15 endpoints are ISO, one test case where all endpoints are bulk. Those kind of things I have to configure here. It depends on test case to test case. And the SRAM is for what you know, right? And what is the other requirement of function interface? Completing what? DMA request. DMA read and write request also what? It completes. What is the other requirement of function interface? Handling interrupt. When interrupt comes, it has to service that interrupt. So what are the three requirements of function interface? Programming registers. Second, completing DMA request. Third is what? Handling the interrupts. What is the functionality of UTMI interface? Doing speed negotiation, doing enumeration, handling data transfer, generating frames and taking care of data transfer. Fourth is what? Taking care of suspend, taking care of resume operations. And also, of course, initial bring up of all the things has to be done through UTMI interface. Any doubts till this point? Can you please read this one? Any doubts here? So SRAM is not the actual pendrive. It is only for temporary division. Now it is the user. I am verifying, so I can keep whatever size of SRAM I need. I can keep SRAM of 256 megabytes. I will divide the 256 into some regions. How many regions? 32 regions. If I am using 16 endpoints, let's say I am only using 10 endpoints. Do I need to again divide into 32 regions? No. So it is me who is going to decide what is the start of each endpoint buffer 0, buffer 1. Endpoint 1 buffer 0, endpoint 1 buffer 1. So I need to do it in such a way that I should not keep too small buffer size for some endpoint, because what will happen? It will become full too quickly. It will become bottleneck again. This is the diagram of UTMI, what I am calling as a phi. On one side, what do you see on left hand side? D plus and D minus. And right hand side, what do you see? Parallel receive data and parallel TX data. You see, clock is also extracted here. Your external crystal is there from DLL and data recovery. You are extracting the clock. You are multiplying the clock, because some multiplier or divisor or whatever, right? It is required because you need to generate the clock, and it is given to whom? Parallel interface. And you are extracting the data. You see, you are receiving the data, putting into HSDLL, putting into elasticity buffer, giving it to multiplexer based on whether it's high speed or full speed. Then it is going to what? NRZI decoder. Data is encoded in NRZI format, and then it is given to what? Bit unstuffer. Then it is put into shift register and shifted out as a parallel. And transmit side is just reverse, exactly reverse of what? This one. Any doubts here? So these are the UTMI interface signals. As I said, UTMI does multiple things. It does speed negotiation, it does suspend, resume, device detection is fine. That's a different part. Then data transfers. So you can majorly divide things into signals that are required for non-data transfer requirements, like transceiver selection, termination selection, suspend them, line state, and operating mode. These are system interface signals. Interface signals which are used for non-data communications. I mean, transceiver select to decide whether you are at full speed transmitter receiver or high speed transmit receiver. Termination select will again say full speed termination or high speed termination. Suspend M will tell whether is the device in suspended state or resume state. Line state will tell what is the current state. Is it in normal operation state? Different things will be there. Then operating mode will tell normal operation, normal non-driving, disable bit stuffing, NRZI encoding. One mistake in what I said. Line state is nothing but D plus D. Operating mode is where I was telling normal operation, non-driving, disable these things. Right? Line state actually represents that SE0, J, K, and SE1. You see, all the things are outputs. Means these are inputs to my device. These are output of what? UTMI. To the file, they are outputs. Which is output? Line state is output. Reset is the input. Termination select is the input. Transceiver select is the input. Finally, device will tell to UTMI what termination is selected, what transceiver is selected, what operating mode we are in. Only thing that my UTMI will tell to laptop is what? My device is what? Line state. Am I sending SC0 to you? Am I sending SC1 to you? Those things. These are the data interface segments. You see, there are two interfaces, data in and data out. You can write the data, you can read the data. For each one, there is a transmit valid, transmit ready. Valid is to tell that I am sending valid data. Ready is to say that other part of device will say that I am accepting this data. In receive, RX valid, RX active. These two are handshaking signals. This data in is for data from core to UTMI. Understand here? 8-bit parallel data from where? Core to whom? UTMI. It's an input. It comes with what? TX valid, indicating what? Data is valid. Who will give TX ready? Core or UTMI? UTMI. It's the output of UTMI. All these directions are with respect to UTMI. So UTMI will tell that I am ready to accept the data. In case of RX, data out 0 to 7, RX valid and RX active. Indicates there is no input. See, when my UTMI is giving data to pen drive, there is no handshaking. It is compulsory that when my UTMI gives the data, my device should compulsorily accept the data. Whereas when device is giving data to UTMI, UTMI has a provision to hold the data, saying that I am not yet ready. Whereas when in the reverse case, it is not possible. When phi, that is UTM, is giving data to pen drive, there is no provision to the device to say I can't accept. It has to accept. Any doubt, please? And RX error indicates that there is some error in the receiving. This is not the exact architecture. Okay, let's do one thing. Given these requirements, can you please come up with the Testbench architecture? I want you to come up with the Testbench architecture. You know how many interfaces it has got? What is each interface got? Interface is only two types, whether master interface or slave. If it is master, you need to connect what? Sequencer, driver, monitor. If it is slave interface, only thing you need to connect is what? Monitor and slave model. It's either memory model or slave model. You know all the inputs. No? Can you draw the testing chart? I hope you remember AHB interconnect Testbench architecture, right? Same thing, just that on master interface, there is only one AHB interface, something like that. On slave interface, APB will become wishbone, AHB will become UTMI, AHB slave will become SRAM. So this will be the first question in interviews, right? Draw the Testbench architecture. After going through AHB interconnect, if you can't come, you need to do some homework. That means. Can you take a look once at this diagram? This is the UTMI agent. UTMI monitor, driver, sequencer, and UTMI sequences. This is the function controller interface. AHB DFM driver, AHB sequencer, AHB monitor, and AHB sequences. This is only SRAM model and SRAM. And all the monitors are connecting to scoreboard and register. That's all. Very simple architecture will be, don't even draw these blocks. Just call it as what? HB master UVC. You call it as what? UTMI master UVC. You call it as what? SRAM model. And just draw the lines from this block to here, this block to here. Then if someone asks, then you can draw UVC means driver, sequencer, monitor coverage. Any doubts you have here? Can you list down the USB features? What all features we discussed? Detection, then speed negotiation, then enumeration, then data transfer, then suspend, resume, right? These are the top level features. Even these features can be further divided. Data transfers can be isochronous data transfer, bulk interrupt, right? Support for multiple endpoints. All this is, I mean, these are the standard questions that will be asked in any interview, right? When you say I verified some device, what is that you verified? Some feature must be been verified. Those features you need to be able to explain. Now, out of these features, what we come up with is called as scenarios, right? If I say this is called as test plan. Test plan is a spreadsheet kind of format where you write serial number, feature. That feature is broken into scenarios. That scenario is verified using a test case. And what is the test case used for that? And what is the steps that are followed in the test case? What is the test status and what is the debug analysis? So for every feature, for example here, my feature is what? Registers. Registers is also one feature. By default feature, every design has a default feature called registers. What are scenarios you have to do? You have to write register reset test, register, write read test. What are the test cases you target for that? Two tests. One is test reg reset, test reg, write read. So what is the intention of this test case? Read DUT registers and compare. Basically, you need to read the DUT registers during what? reset values. What is the second test will do? Write, read and compare. How do you do this first test, register reset test? Keep DUT in reset. Rather you say apply reset to the DUT. Then what do? What do you do? Read all the registers and compare with the spec reset value. Test status, you need to run this test, passing or failing. Why it is failing, like that. Then you go to next one, device detection. It's the next feature. What is the scenario? It's a 5-level feature, need not be covered at USB 4 level. Next, what is the next feature? Speed negotiation. We discussed about how many possibilities? 4 possibilities, right? High speed host and high speed device. High speed host, full speed device, full speed, like that. For each scenario, there is a test. You can see how we are dividing each feature into scenarios. You should not memorize this. You should try to understand how we came up with the features at top level, how each feature is being broken. I mean, there could be another 4 or 5 scenarios. It was only prepared as a template to just help you understand, right? So each test case will have a specific steps. How do you do? Configure UTMI agendas for what? High speed operation. Device need to be configured in high speed. Initiate speed negotiation process. Data transfer should happen where? In the high speed mode. Like this, you write for all this detailed steps. Detailed steps will tell how you are going to target test step by step. Because randomly, it's not like in AXI, VIP or AHP transaction where you randomly generated 5 transaction or 1 sequence, right? You need to know intention why you are writing a sequence. What is that sequence should do? That will be only understood by understanding these steps. Then enumeration. What is enumeration does? Read all the descriptor info in the design. So what are the different test cases? Test enum. Test enum for device descriptor, configuration descriptor, string descriptor, interface descriptor, endpoint descriptors. What is the flow? Test case targeting reading device configuration, interface and endpoint descriptors. Test targeting device descriptors. Basically, we read and check whether we are able to read the descriptors properly or not. Next, data transfer. Even in data transfer, what are the 2 major features that are possible? Full speed and high speed. Now, and data transfer while you are in suspend mode. Let's say you are doing data transfer and you initiate suspend. Something happens and it enters in suspend. Then device install or NAC phase. I mean, you are doing data transfer, it is issuing NAC to you. Right? So then test all transfer. What do? Even when it is in full speed, you can do bulk transfer, you can do isochronous transfer, you can do interrupt transfer, you can do mix of these transfers, you can do in transfer, you can do out transfer, you can do 15 endpoints isochronous, you can do mix of these things. So many things you can try. If you write like that, if you write combinations, some thousands will come. But you can't target 1,000. It's all about optimizing your test cases, still covering maximum possibilities, all possibilities. So to take care of this, we have something called as functional coverage, which will tell have you checked all the possible combinations. Like this, you write down all the combinations. So suspend is one feature, resume is another feature. So when you look through the spec, you'll get more features like this. For example, let's say core operates in USB OTG. If core capable, it becomes what? Another feature. All these things you have to check up on it. So is it clear how I came? That document is there in the course material, test plan or something will be there. You just take a look. Why this is important is when you go to interviews, the first thing they will be asked is what features, what scenarios did you verify, right? You can't say that I verified everything, then you will be only confused, right? When they ask you to create scenario for speed, you need to know what test cases you are comfortable with or what scenarios you are comfortable with. Accordingly, you need to tell that I worked on only on these features. I only worked on function controller side. I only worked on SRAM side. I only worked on UTMI side. I only worked on reference model. If you have done complete environment, then you can say I've done everything from spec to closing verification. Then if you say that, you should be comfortable. So this test plan is to give a basic idea how you can categorize your preparation. Right? If you are comfortable with everything, then it's fine. In some cases, you may be asked to list down the test cases also. What test case did you target? So far we have done with what? Came up with the Testbench architecture. Right? You need to go home and prepare that architecture. Even it's there in the material. You need to come up with the test plan where you list down features, scenarios, test cases. Then what each test case, why this test plan is important is why understand test case is important. It tells you exactly what, tell you that you should apply this. Then you should configure it. Then you should initiate speed utilization. Then you should start doing the data transfer. That detailed steps it gives. That will tell you what you should do from device side, sorry, UTMI side, what you should do from function controller side, what is SRAM responsible for. All these. Any doubts till this point? So when we meet tomorrow, I mean, I'll give you what all documents to read. You can see that there are basic documents like USB doc. USB doc is the specification of the core we are doing. You can see that in the document, there are different sections like introduction, architecture.
Yes, sir.
Architecture. What is the host interface does? What is the memory interface arbiter does? Yes. Then it will say what is SRAM interface does? What does protocol does? What is protocol layer further divided into assembler, protocol engine, packet assembler, DMA interface, everything. You have to read this quite clearly. At least 1-2 times you have to read. Then what is protocol engine does? Then what is packet assembly, DSMA, what is UTMI, everything it goes to explain operation, how it actually works, where is used, what is the need for purpose, what is endpoint, what is the USB function. This is how you can understand physical function. Then what is the endpoint, why we need buffer transfer. Then it talks about how buffer transfer is used in storing the transaction. Then what happens is setup stage. You see, USB host will send setup token. And the USB host will send data packet. See, control endpoint itself happens in stage, data stage. There is some noise from one of you. You need to be mute, please. See, as I said, during enumeration, I said we use what? Control data transfers. The control itself happens in 3 stages: setup stage, data stage, status stage. What are the 3 stages? Setup stage, data stage, and status stage. In setup stage, setup token is given from USB host to IP. Then data is also given from host to IP. Setup is to tell that I'm going to read this descriptor or something like that. Then IP will tell that I'm okay to give something like that. It gives acknowledgement. During the data stage, you give in token, indicating what I want to read this descriptor. You are initiating a read request. Data will go from where to where? IP to. Then it will give acknowledgement. Then what is status stage? Out token. You are giving what is the status? Have you read successfully those? Then acknowledgement packet. Now you need to understand more. You need to read more deeply into USB code to understand what is this status stage does, what does data stage does, what does setup stage does, everything. Right? Like this, it is explained for all the types of endpoints. DMA operation. What is DMA operation? Then what is PID sequencing? Then for each type of, for full speed and high speed, if it is isochronous, what are the requirements? For interrupt, what is the requirement? Bulk, what is the requirement? Then what is the bit time? Just a quick summary of whatever happens in full speed, whatever happens in high speed. So then it talks about, you see, in case of data PID, if it is isochronous data transfer, you can, if it is transaction is smaller than 1024 bytes, you only use data 0 type of data packet. Even data packets are 4 types: data 0, data 1, data 2, M data. If it is between 513 to 1024 bytes, 2 transactions, if you want to do 2 transactions, use data 1 to data 0. If it is 3 transactions, you use data 2, data 1, data 0. For out endpoints, you use M data. Then how it works for interrupt transfer, bulk transfer, then how packet errors are taken, packet with bad CRC ignored, no action taken. It clearly tells what you should do when some error happens, then all those things. Then special packets, out to endpoint, different aspects it talks about. Then when a packet comes, how it is handled. Token packet comes. Let's say received token. Is the token corrupt or not? If it is corrupt, what? Report token error. Else what? Decide token. What is the token type? Is it a special token like ping SOF token? Is it a setup token? Is it a in token? Is it out token? Unsupported token type. There are some combinations where token type may be unsupported also. Then if it is special token processing, if it is special token, you have to process like a special token, special packet. If it is setup token, you have to perform what? Setup cycle, setup stage, data stage and status stage. If it is in means you have to perform in data. If it is out means out data. Then these are continued. If it is special, it is explained here further. This is special token processing. Then in data cycle here. Then out data cycle. Like that for everything they are clearly explained. Then this next 2-3 slides will talk about what? How USB is brought up from reset, then moving to full speed, then how does it move to reset, how does it move to suspend, then how does it move to suspend negotiation, how does it again move back to normal operation. Everything this flowchart will clearly tell. Then what is suspend resume, how do you take care of that. Then registers, there are totally 70 registers actually in the design. CSR is a common status and control register. FA means function address register. You see, I said for every core, we give 7-bit value. Who will give ideally? Host will give. But in our example, we are going to perform that right. Host controller will, function controller will write in our case, right? Interrupt mask, interrupt source. What interrupt got generated? Should it be considered or should it be ignored? Frame number and time. What is the current frame number and what is the time? Then UTMI vendor. These two are not significant for us. At least frame number and time is only for status purpose. It needs to keep track of what frame number came, what is the time. UTMI vendor is only for people, the company which is providing UTMI. Is it Intel? Who is providing UTMI? Those kind of things. Then these registers, you see, these 4 are repeating everywhere. What is the first register? CSR. Second is what? Interrupt register. Third is what? Buffer register 0. Fourth is buffer 1. Like this for all the registers we have. And then each register is divided into fields and explained in detail. So going forward, as I said, we'll be developing register model for these registers. Then core IOs. We said 3 IOs, right? 3 ports. One is host interface, that is in our diagram I have shown what? AHB, but it will be replaced with what? Wishbone in our cases. In reality it is wishbone, but when you go to interviews, you can explain them that you have worked on AHB. It looks more real project. Then you have what? UTMI interface. As I said, we discussed, right? Status signals and system interface signals and data interface signals. So these are system interface, some of them are system interface, some of them are data signals. Then buffer memory interface, the third one, SRAM interface. Only SRAM has only few things: address, data out, data I, read enable, write enable. Then appendix. How do you configure the design to have only 9 endpoints? How do you remove other endpoints? Just basically talks about how to work with the design if you want specific requirements. Then this is how design hierarchy looks like, our RTL code. RTL, first file you have is what? USBF top.b. Below that you have 3 files: UTMI interface, memory arbiter and wishbone, and the protocol layer. What is that UTMI interface has? UTMI LS. Then what is protocol layer has? Dissembler, assembler, internal DMA and protocol engine. What is that memory arbiter has? Only that file. What is that register file has? Individual registers definitions. Like this, everything is clearly shown here. Then appendix C, it talks about how SRAM write reads happen. When we are going to develop SRAM monitor and SRAM model, we have to use this convention. Because core is assuming that this is the timeline diagram SRAM is going to follow. Accordingly, only for this rule only it is going to drive the data. So my model also should be using the same concept. Because even though I use the term SRAM in real life SRAM has very complex structure, right? Many signals will be there. So if they don't give this kind of definition, people can draw their own inferences and they can implement their own SRAMs, which is not right. So they have given this description also. UTMI 5. What is UTMI 5? How it works? So this section you can ignore, software model and all this you can ignore. So till page number 50 you can read, 50, 55 you can read. This is about core. Then you need to understand a little bit about USB logic, right? How it works. This document will talk about what is USB is all about. What is full speed means, what is high speed means, what is low speed means what. Then what are the connectors, what are the two types of connectors, what is 4 pins, what is each pin means, V plus, D minus, D plus ground. Then how detection happens, how suspend happens, how do you enter suspend, how do you exit suspend. Then what are the different types of packets, then what is the data packet structure. For example, you see here, this is the token packet structure. For our verification purpose, sync and EOP can be ignored. Why it can be ignored? Because we are modeling at the UTMI level, we are not modeling 5 to 5 level. That is where sync and EOP is required, because they don't have any separate signal. Whereas at our level, we have a TX value, TX ready, RX value, RX active. This is how handshake packet looks. This is how data packet looks. Everything is clearly explained. Then how USB function works. See, one device has 2 endpoints. Other device has what? 3 endpoints. This device address is what? 2. This device address is what? 3. This is what is actual function control. This is what is the host. It is the one which keeps sending frames. Then endpoints. What is significance of endpoints? Endpoint types. Right? How does setup happens? What is status stage? Everything you can read this. It clearly tells you what is meant by in status, out status, all those things. Then each transfer. What is control transfer? What is interrupt transfer? How it actually happens? Then what is isochronous transfer? So these two documents if you read, you will get pretty good idea about USB 2.0. Right? So you don't need to go to this level. You can probably stop at page number 18 or 19. That will give you good idea about what is USB 4. Then you can also spend some time reading this document. So please do this before you come to tomorrow. I mean, I know it may not be possible to read both the documents completely, but try to get a top level overview. Now that we have already done USB core presentation, you should be able to understand things more easily. So let's stop the session here. When we meet tomorrow, we'll continue with the revision of this one. Then we'll start developing the Testbench components. Then we'll start implementing scenarios for speed negotiation, data transfer, suspenders, and all those features we'll try to. So